Good afternoon, everyone. Today we're going to solve an equation using some trigonometry, and our equation reads 4 sine squared x is equal to 3 tan squared x minus 1 for all solutions in x being a real number in degrees. So, at first glance, this might look daunting, but my best word of advice is to simply start writing what you know you can write in order to simplify something, just to kind of get your momentum going, okay? Now, for me, that meant writing tan squared x in the form of sine squared x over cos squared x, because I know I have a sine squared x over here, and so maybe that'll get us somewhere, at least. So let's write the left-hand side as is, and let's rewrite our tan squared x as sine squared over cos squared. So we'll have 3 sine squared x over cos squared x minus 1, okay? Now, at a time like this, it's not always obvious what the next step forward should be. There's going to be a lot of trial and error, backing up, starting over, kind of getting a sense of what the best path forward is, okay? Take your time. If you want to pause the video, try it on your own, and then check in as you're working through it. Feel free to do that. I encourage you to do that. But if you want to move forward, what I decided to do here is I wanted to get rid of our denominator altogether, because I know that equations with denominators are harder to solve. Now, because we already have a denominator present, we can go ahead and multiply both sides by our denominator, which means multiplying both sides by cos squared x, okay? Since we're multiplying both sides by cos squared x, we're not running into any potential issues of dividing by 0, right? We are going to see the cos squared x getting canceled out with this factor on the outside, but again, because we are the ones doing multiplying, we're not at any point risking dividing by 0, and so we avoid any potential issues in that sense. So if we go ahead and expand both sides, we'll have on the left-hand side 4 sine squared x cos squared x, and on the right-hand side, the cos squared x is going to cancel out, and so we have 3 sine squared x minus cos squared x, okay? What I decided to do here was I decided to write cos squared x as 1 minus sine squared x, just playing around with our first Pythagorean identity of sine squared plus cos squared equal to 1. Okay, you're going to have to get very familiar with those trig identities to kind of unravel these harder equations. Okay, so now we have 4 sine squared x cos squared x is equal to 3 sine squared x minus bracket, don't forget your bracket, don't make silly mistakes with negatives, super frustrating way to lose marks. And now, if you have a look at the right-hand side, we have no more cos squares, we have only sine squares, which might be a good sign, we'll see. But let's go ahead and simplify this a tiny bit more. So 4 sine squared x cos squared x is equal to 3 sine squared x minus negative sine squared x, brings us to, again, 4 sine squared x, 4 could be something, coming together, and then minus 1, okay? Now, what we do from here is, again, not obvious whatsoever. But after a few bouts of trial and error, what I found was that rewriting once more cos squared x as 1 minus sine squared x over here on the left-hand side, writing cos squared x as 1 minus sine squared x, again from that Pythagorean identity of sine squared plus cos squared equals 1, this allows the entire equation to be written in terms of sine, and no longer do we have any cos present whatsoever. And so let's see how that plays out. We have 4 sine squared x times 1 minus sine squared x, right? Replacing cos squared with its equivalent to 1 minus sine squared is equal to 4 sine squared x minus 1 on the right-hand side. And you might start to see where this is going. If we go ahead and expand this out, we'll have 4 sine squared x minus 4 sine to the power of 4x equals 4 sine squared x minus 1. And now we might notice, if we take the time to take a breath and see what's going on here, 4 sine squared x is common to both sides of our equation. So we can subtract it from both sides, right? And it completely goes away. And so now we right away get to simplify our equation to -4 sine to the 4x is equal to -1, right? Because the sine squares completely got rid of one another on both sides of our equation. And so now we end up with one term only on the left side, one term only on the right-hand side, and this is getting doable. Let's go ahead and finish off with some basic algebra. Divide by -4, divide by -4, and I'll bring you over here to finish up our solution. So now we have sine to the 4 of x is equal to 1/4. And now, similar to what we do with the square, we're going to take the 4th root of both sides, but we have to remind ourselves that when we take the eventh root of a value, we have to consider the positive or the negative version, right? And so we have that sine of x can be positive or negative, the 4th root of 1/4, and the 4th root of 4 is like the square root of the square root of 4, which is the square root of 2. And so this is positive or negative 1 over the square root of 2. And if you are familiar with this, that's great. You might be more familiar with the equivalent way of writing 1/2, which is as root 2/2, more commonly seen on unit circles. And so now let's not forget our plus or minus, always, right, at every step of the way. And so now we're all the way down to solving sine x is equal to plus positive or negative root 2/2. And considering all of those options for all real numbers in x, we get the solution we want in degrees. So the first one, x being the inverse sine of root 2/2, and secondly, x being the inverse sine of negative root 2/2. And if you're familiar with those values in your unit circle, that's going to provide you with the set of solutions. X is 45 degrees, and the following solutions would be 45 degrees plus or minus 90 degrees in either direction. We would get 45 degrees, 135 degrees, 225 degrees, 315 degrees, because positive or negative in sine means positive or negative, right? Top half of the unit circle, bottom half of the unit circle, all 4 quadrants are considered, and we know that root 2/2 are always in the middle of the quadrants, and so that's 45 degrees plus or minus. We can just add or subtract 90 degrees in either direction anywhere along the way infinitely many times, because we're grabbing all possible solutions. And so we have 45 degrees plus or minus 90 degrees, let's say times k, where k, we're already considering adding or subtracting these integer multiples of 90 degrees, and so k can be restricted to any whole number. And I apologize for the diagonalization of my writing, but this would be our complete set of solutions. So I hope this helps. I hope this kind of helps give some believability maybe to a somewhat daunting equation at the start. And just a reminder that just getting started with writing the simplest things that you know that you can write, just to get yourself started, just to build some momentum, slowly, one step at a time, rewriting things in convenient ways that you know how to write, slowly putting things together, simplifying down, and then finally allowing ourselves to be able to solve a much simpler version of the equation that we started with. hope this helps. Thank you so much for watching, and have a great day.